It's up to you. Alex, I haven't heard that. It's like 6 months.
Yeah. My only issue is what between. They also see it.
Yeah. Yeah, nothing. I'm really going to, it's like on the way to like today, so I was like, oh, we're actually now my goal is. And they're like, just heat up there. So I have random scans that they're really actually, if you like, from my, you like, just wanna look at my.
Right, so why don't we get started on this? Anyway, it's the homework's all on a surfactant system, you know. So anyway, I brought this stuff in. I don't know if this will work, but so it's basically like kind of like shampoo stuff, right? So that's shampoo. It's like that's a viscoelastic fluid, like a shear thinning fluid. So it's kind of, and you know what it's like when you get it in your hand or something. And that's oil, right? That's just like olive oil. So it's a Newtonian fluid. Anyway, so you got like two kinds of fluids, shear thinning fluid and a Newtonian. So no matter how hard you shear the olive oil, the viscosity stays the same. That's the idea, right? And then this would be like maybe an oil additive, like you add polymeric additives to oil to make it, so it'd be kind of thick when the motor first starts and like it doesn't leak through the seals, and then as it speeds up, you get less friction, so the viscosity drops. Right, so polymers are good for lubricants like that. For shampoo, like you want it to make like almost a solid in your hand and then put it in your hair. So in order to smear it around, the viscosity has to drop. Otherwise, it would be like putting grease in your hair. So it'd be hard to smear it in, whatever. Right. So the other thing is that you want it to. So this is a polymeric fluid, but it's like it'll dissolve. Like you add more water, then you reach the point where you're above the you're below the critical micelle concentration. So there's a point as you increase the concentration of the surfactants, like these chains that have like a oil part, so an alkane, just a carbon chain, and then some kind of polar group on the end. So you can reach a concentration where they don't form micelles. So they need to have a certain critical concentration to form these spherical micelles that will encapsulate the oil and stuff, right? So anyway, so if you dilute it down when you wash it out of your hair, then it just goes, this will go into solution. Goes back into solution. The other thing about these is that they'll phase separate into a crystal. So they'll form, if you concentrate it too much, it'll crystallize. And it makes like a gooey, icky crystal, right? Because of low molecular weight, gooey stuff. And you can also reach that by dropping the temperature. So you reach a temperature called the Kraft temperature, where the micelle precipitates out into a crystal. It's like a cloud point. So it's basically, they talk about in solutions, you talk about a cloud point. When you reach a point where it phase separates, the stuff becomes milky, not cloudy. So anyway, that's called a upper critical solution temperature, because if you look across concentration, there's like a peak in it at the top, so, and then it's two phase at the bottom. So it's called upper critical. And the other kind is a lower critical, where you heat it up and it phase separates. So we'll talk about that later on. Somewhat. Anyway, so we get these two things. So I was going to mix them. We get like, so if you're making, I didn't have the popsicle sticks. I got the spoon. I use a handle. So if you mix these two, so you get two phase, like it'll just form a solution. Oils, I guess the waters, the oil should be less dense, but it goes, I guess it's on the top. So it's a two phase, right? So anyway, if you take that and then if you kind of mix it, it gets a little bit cloudy. And if you keep mixing it, so there'll be a point where it just all of a sudden turns like all white. You know, and then it becomes basically a Bingham fluid, which is like ketchup. Like it doesn't flow unless you whack it. No, it's the kind of idea. So it's It's not shear thinning anymore. So this is basically becomes like Procter and Gamble product, like something like a cream you're gonna put on, or a shaving cream or something, or if you put in fluoride, it's toothpaste. I mean, basically everything they make is made by that process. You put in like a little bit of surfactant, a bunch of oil, or you can put vary the amount of oil and surfactant. But that's kind of the idea of most consumer products, is making something like that. So anyway, I mean, I can kind of see, it's not thick enough that I can turn it upside down, but see, it's still got a meniscus that tilts when I tilt it. So it doesn't really flow unless you whack it and it'll flow. So that's like the basic three kinds of fluids actually in one thing. It's like the shear thinning, polymer viscoelastic fluid, Newtonian fluid, and a Bingham fluid, right? Anyway, so this is also like how you make mayonnaise. It's like, this is a surfactant, kind of like this in the shampoo. It's like sodium ether lauryl sulfate, so SELS. So it's an ether on the group, but it's basically a 12 carbon chain, which is like beef lard. That came from beef lard with a glycol head group with 3 tails on it, so triglyceride. Then you break those and you get a carboxylic acid. And then if you put NaOH in it, you get a soap. You get soap like NaOH head group. So it's a polar head group. Then the OH is minus and the A is a counterion. And then that soap will make micelles. Also, if you stick that in with sulfuric acid, then you can sulfonate it. So those are both exothermic reactions, like highly exothermic. So you have to cool it when you do that. And then so the big problem, one of the problems is like you got to put a lot of water into it. So that this shampoo is going to be like 3 to 5% surfactant and the rest water. So you're like shipping water all over the place. So people complain about shipping water. So they want something more concentrated. But when you concentrate it, you reach this point where it crystallizes out, right? So that's like a problem with soap. So the Procter and Gamble marketed these like concentrated detergents for laundry, right? So okay, what that is, it's got this benzyl sulfate. So you take benzene or toluene. So toluene, it makes this toluol thing. Toluate, sodium toluate is a toluene sulfate. So you add a sulfur group to a pair of position of toluene, or just a sulfate group onto a benzene ring. And that's an exothermic reaction too. So all these things are like pretty easy to do. But they're all right. But they're all like carcinogens and toxic. So there's like 2 companies in Cincinnati that make benzene sulfonate or sulfonate, I guess. There's one I went to up. It's kind of like I don't know. It's off 275 and off. Maybe we used to have co-ops that work there. So it's like they have trainloads of benzene that come in. So this is like P&G spinoff, right? They want to make concentrated detergent. They don't necessarily want to handle a lot of benzene. So they hire a company that's going to take trainloads of benzenes and then trainloads of sulfuric acid, and then a big bucket that's cooled, and then dump it all together. So, I mean, it smells like benzene and it's really hot, like it's exothermic reaction. And you take that stuff and you just add it to the detergent. It does kind of what these guys are saying they're doing here, more or less. Like you have these groups that concentration would phase separate out, but then these benzene sulfonate groups kind of pack in, somehow. This is all this surfactant stuff is like a geometric thing. Like what's the geometry? So it's going to be kind of some kind of a triangle or parallelipid thing. It's thinner at the oil part and fatter at the head group part, because the polar groups are larger, I guess, and they have more kind of steric kind of or polar coulombic repulsion type things going on. So this spreads out, that's thin, so it will tend to make a sphere. Right, and then if you pack different things in, like salt, so there's a counterion also. So the salt, if you add salt to the solution, it affects the counterions. And when those shift out, this thing somehow makes ellipsoids. It can be geometrically calculated why that happens. And if you keep adding more salt, it'll make these long fibrous things that are going to look like. So this paper has some pictures of that. It's a pretty simple paper. He says like, first he says like it by adding this stuff, I get a single, it doesn't phase separate, even though, so it's kind of weird that he shows this picture, because this one looks phase separated, it's cloudy, like that means it's phase separated, but anyway, he claims that all those are one phase. Then he's got this is typical of what people are going to do in this field. So they get worm like my cells and they kind of demonstrate it by doing a TEM. So these lines are supposed to be the worm like my cells. And if you look closely, so you can see some features of this. At some point in here, you can see, so there's end groups. I'm not sure that's one of them. There's kind of end groups and there's the chains. And then there's something like entanglements. And then there's these things are branch points, right? Like right there, there's a branch. So that normally, if you take a polybutadiene rubber and you make a rubber out of it, or polybutadiene polymer and then cross-link it, so it's got vinyl groups in it that'll pop, and you can bond the chains together and make a network, right? So normally the viscosity will go through the roof once you did that. Once you start like radiation polymerizing polystyrene and you get random cross links at it, and then the viscosity goes through the roof and it quickly goes to kind of infinity. Like it doesn't flow anymore because it's a gel, right? So, right, but in these materials, when you have these branches that show up spontaneously, so they just somehow show up as you get to higher concentrations, you get branches, these things reduce the viscosity. Because in this case, so these branch points, because the thing is this structure, right? So the thing is this, it's not really a polymer. So basically those branch points, there's no impediment to the branch points just migrating along the chain. Like you can take somehow, this is a theory, but basically it can take these molecules and like transit them into the branch part or into the chain part, so it can like heal itself all the time. So the branch points are mobile. In that case, adding branch points kind of looks like it chops the chains to be shorter. That's the theory. That's the theory of this guy, Mike Cates, who's like kind of he's at Cambridge and he's kind of like Nobel laureate candidate, whatever. I mean, everyone sees him as Nobel laureate. So this is another paper that just came out. Well, I guess 2023, but anyway, so Cates is a kind of a big name guy in this field and also across polymers, and Larson's another big name guy. He's at Michigan and he does rheology. He's done a lot of rheology on these worm like my cells. He's a polymer guy, but he does a lot of his work either in polyolefins and this kind of stuff. So you can see they have this shear thinning behavior they show somewhere. Oh, I'll talk about this after. So Larson wrote a book called Complex Fluids. So if you're interested in this subject, take a glance at this book. It's a pretty easy, I think it's not that bad of a book, to look at. He's a chemical engineer, so that automatically means it's going to be talking your language. And then I think he's dual like chemical and materials. So anyway, so it's got, like you can see, he's got like my cells and stuff. He talks about polymer, whatever. So if you flip through this book, you'll see different things. So probably worth looking at that too. All right, so anyway, back to this thing. So there's these branch points that are kind of weird here. And then there's actual entanglements that show up in these micrographs too. So usually what people are looking for in entanglement is it's like tangled hair. These are also called hair like my cells. So the tangles are kind of what lead to this viscoelastic behavior, right? So there's some debate over what an entanglement is. So basically, it has to only be that there's some association between the chains. So it doesn't have to be a topological link like that. But mostly everyone, when they think about it, think that it's, if they're going to draw a picture of it, that's what they draw, is this kind of looping together of the chains. So you kind of see that here, I guess. So that's probably a branch. So branch points, I think, should be the same color. In other words, the darkness here has to do with the electron density that you're looking at in a transmission mode. So if it's the same color, that's a branch point. If it's darker, that means two of them are overlapped because you have more stuff there to kind of absorb the extra electrons. right? So it's like here, that's definitely overlap, so it'd be like an entanglement. And then that's probably a branch point, right? So, right, you can spend a lot of time looking at micrographs of these if you want. An important thing to remember is that this probably does not represent reality, because the way they make this, if you read how he says how he made it, he takes liquid ethane minus or 70K or something. And then you take, so carbon, TEM, you have a holy carbon grid, they call it. So it's a piece of carbon with holes in it. And then you dip it into the soap water, and then you let it kind of stretch out in the holes. You'll get a meniscus of the surfactant, and it stretches out, right? And it's gonna, then you dip that into minus or 70K and freeze the whole thing. Then you keep it frozen and you freeze your TEM. So all the TEM finger that goes into the microscope is also at 70K. So everything's like super frozen. So so basically, in forming that meniscus, it's just the thinnest point. So in TEM, you have to look through water, you have to have a very, very thin slice of it, like a nanometer thick slice. And these things are nanometers size tubes, right? So basically, whenever you cram a nanometer size tube in a nanometer size sheet, it's got to deform it somehow, right? And also the process is that you stretch out, like meniscus formation is like a drawing, like a two-dimensional biaxial extension of the film, which is going to make them all stretch out, right? So basically, when you look at this kind of micrograph, it's really important to look at like the conditions under which it was made. And in this case, these are really severe conditions, right? So squishing it down into a film, it's the thickness of the thing that you're looking at. Again, it's like the ant, smush it, and then you take a picture. It's like, is that having to do with the ant walking around or anything, right? So anyway, so that said, what people do instead of that is, and the advantage of aqueous systems is that you can get heavy water, D2O, right? So basically you take seawater, so deuterium is twice as heavy as hydrogen, right? So you can take seawater and just spin it in a centrifuge. If you spin it enough and do enough cycles of that spinning, you can separate D2O from H2O. And that's how you basically get deuterium. Like you break down the water to get deuterium after that, and then you do other chemistries to get deuterated, whatever. So the advantage of deuterium, if you look at IR, it weighs twice as much. And IR is like the radiation comes in and kind of wags a dog's tail. And the dog's tail weighs twice as much, it gets half the frequency. So basically in IR, you can pick out the deuterium things. And it's also useful in NMR. It doesn't split the NMR proton NMR, you split the protons split each other, and deuterium doesn't split another proton. So you can tag molecules in NMR to see different features to deuterium. And the third most popular thing is to use it for neutron scattering, because deuterium and hydrogen have the furthest contrast differences of anything, of any material. And deuterium has a negative contrast and hydrogen has a positive. It's like having a negative index of refraction and positive. So the furthest apart of any two things, if you put your worm like my cells in a dilute condition into deuterated water, they light up like red, whatever, like glow in the dark, whatever. So you can see them, right? So basically you can do neutron scattering and get the structure of these things with deuterated water. So it's pretty simple to do that. And it's also looking at the worm like my cells kind of in their natural state, not in this kind of weird squished ant state, right? So that's kind of that's words of wisdom, I guess. And then so what they did was there's a problem with this molecule, wherever that is here. So this is a tertiary amine, this 4 bonded nitrogen thing, right, with an ion on it. So right, so that's a typical one of those is a typical head group for a cationic surfactant. Right, so you can have negative, so these SLES or SDS, sodium dodecyl sulfate or sodium lauryl sulfate with 12, and then a sulfate group, so Na plus, and then the sulfate's minus. That's an anionic surfactant, like this one, right? So that's an anionic soap, really. So this would be like, soap would be like this, like a 12 carbon chain, this carboxylic group, and then a sodium. So you just added NaOH to the carboxylic acid, and you have this thing, right? So, right, so that's soap, and that'll crystallize and make a bar of soap, right? And then you would sulfonate that to make really a detergent, right? So Anyway, so they're mixing, so anyway, this thing crystallizes out, so it's not as good as it could be for kind of general use. So they add another quaternary amine to this thing. Right, so the double amine stabilizes this in solution. It makes it so it doesn't precipitate out, and that's why he shows this picture of it doesn't precipitate out. And then they add this anionic group. So when you add an anionic and a cationic, they kind of couple together because it's plus and minus. Right, so he's saying that it forms this thing. Doesn't really give any evidence for that, but he just says that's what happens, and that's why it behaves. It makes form like micelles better when it does that. I mean, you can see that that's going to crowd the head group region and not crowd as much this region, so it might change the shape of the thing, and you can manipulate whatever you want. That's kind of the idea of this thing. So it's kind of a trivial paper. There's not really anything profound here. The thing that they did that's new is they added on another tertiary amine. So these things cause genetic defects in people. They've shown that it causes genetic defects. So it's in cosmetics and stuff. So there's a lot of talk about that. And the other thing is that some people are allergic to tertiary amines. So for some people, it will cause like a rash or something. So I have a face cream, oh, my face turned all red and blistered. And it's like, yeah, don't use those. So you have to kind of look on the label if it's got tertiary amines. So they kind of have a bad name, and they, whatever, all over the place. But nonetheless, they're marching on and putting another tertiary amine on the thing. So it's kind of a little twist of his paper that's an odd thing to do. Anyway, so other than that, he shows that it's viscoelastic, so that's good for us. So he's got shear thinning behavior, right? And it changes with the concentration, but it's like markedly different than what you see for polymers. Well, it depends. So it kind of looks different than the polymer curves that we saw in class, wherever that was. Or in, I guess Larson doesn't have that, but we had a picture of it here somewhere. So we had this curve. That's a monodispersed polymer. These things are polydispersed. So it's got a power law decay. So it's log-log, so that's a power law decay. And it's got this Newtonian plateau. So he's got something like that, like a Newtonian plateau. And he's going to work with that Newtonian plateau value over here. So he's going to pick that off and plot that against whatever his parameter is, which is concentration here. So we got the same plot here. This plot. This is the zero shear rate viscosity, that plateau number versus log plot. And it's linear. So like this has a slope of 1. So you can say slope of 1 means 1 decade by 1 decade. So you can pick off like that and that and draw a line here. And that's a slope of 1. It should be the same as that slope. Then you see entanglements happen. So these are oligomers to the left, and these are polymers to the right. Then this thing shoots off with a 3.4 power. That's a nice clean transition. That's the entanglement molecular weight. And for all the polymers is about like 100 chain units, or about 10,000 grams per mole. Is where that transition happens, right? So the chains, because they're long enough, you can think of it that they can kind of flip back and then they get hooked together. In reality, there's a lot of debate over whether entanglement is a hook together or some other kind of interaction, right? So, but the other kind of interaction is never specified. So that makes it a little hard to make that argument. But anyway, so here's his thing. So power 1, you can draw a line over here, and draw a line straight. There'll be a power 1. You can make an argument, well, this is kind of acting like an oligomer, I guess. And then maybe, and then you're looking for, in concentration, we're looking for a power 3 here. So it would be like 3 decades to 1. So you go like that, and you could kind of argue the power 3, but there seems to be kind of a gap here. So it isn't exactly a clean thing that you're looking at. Let's see, I should have showed that this is the concentration one. So this is linear, that's about a power 3. They can say like 1, 2, 3 decades and 1 decade. So actually it doesn't look like it, but it is. This should be 3. So anyway, so you can kind of compare those. That's kind of the point of the homework, is to just say that, like look at those 2 plots and the 2 plots from the sides, and like they're different a little bit. They're the same kind of too. I mean, for one thing, he's going across concentration here, not molecular weight. If it was molecular weight, they would all be on top of each other, and then so the tail over would come and then they'd be at the same line over here. Like this part would overlap and this part wouldn't. So the plateau would change with molecular weight, this part wouldn't. With concentration, it's a little bit different, especially for the system, because as you increase the concentration, the molecular weight is supposed to increase of these things. And that's something that Kate's came up with, this guy, like in this other paper, this thing. Where that is, yeah, this paper. So anyway, so you can kind of look at those two plots and get something out of that. What else is in here? And then as he gets to, so here in this plot, so he's got viscoelastic behavior for these things. And then if you go to low concentration, so these are the ratios of this cationic surfactant with the two tertiary amines on it, and then this soap, right, the anionic soap. And then, so the ratio is like 1:1, or then you add more soap to it. So more and more soap. As you add more soap, it becomes more like a worm like micelle. When you add less soap, so 1:1, and at low concentrations, it becomes like first at really low concentrations with the 1:1, it's just like nothing there, like it doesn't form anything, right? There's no, I don't know, I guess they didn't get viscosity measurements or something, and then it doesn't behave right here. And then you get to a little bit higher concentration at 1:1, and then it's kind of almost like, it looks like between those two, you get a Newtonian fluid. And then it's kind of trying to get a worm like micelle, but it hasn't actually done it. So something else is going on. And then once you get to the higher concentration, boom, it forms worm like micelles. And as you change the ratios of the soap and the cationic surfactant. So anyway, you can see the games people play here. There's nothing really special about what they did. This is kind of what people do with surfactants. I mean, it's typical study. So what else is in here? This part I'll talk about if we have time a little bit today, but it's not in the homework. It's just a picture and that's it. So it's a pretty short paper. It's kind of like simple. I mean, I think it's simple, but you might think it's really complicated. So it's a difference of opinion here. But basically, hopefully figure out to get out of this, basically just to say, a little bit about surfactants, and how, about polymer rheology, something about polymer rheology, and something about the surfactant field, which seems to be, at least one person is working at TNG or something. Right? So, but I think you run into surfactants. I mean, if you're at Lubrisol and you make grease, okay, so grease is an oil, like a Newtonian fluid oil, and then mixed with some, it's kind of the same kind of thing, like mix it with some surfactant, and you can make grease. And then mayonnaise, so you take egg, which is going to have kind of surfactant, complex biomolecules in it, but act as surfactants. Then you add that to oil, and then do the same thing I did here, and you make mayonnaise. And then what else? Basically, you can make anything that looks like that in a way, So it seems like if you looked at mayonnaise and you said, like, how is that like egg and oil? Like the two things don't make something like that at all. But then you realize like there's a lot of structure in it. Like this reason it's like that is because it's forming these complex structures that can percolate through and make kind of a network in it. Right. So it's so anyway, so a lot of different things are like that. So it isn't just surfactants. It's like all these products and things that you run into are made that way. So anyway, so that's that business. Tells how he makes it. So then the other thing here is that all these names are like insane, right? So N1, 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 N3, 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 pentamethyl, N3, 3-stearoimidopropyl propane, 1,3-diammonium bromide. It's pretty simple. So they just call it C18DQA. But if you look at for all these things that are like that, like you look at it, oh, it's a 16 carbon chain, and then it's got a double tertiary amine on it, and it's got this carboxylic on it because it started as lard. Like this part is lard, right? This part's oleophilic. This part is hydrophilic. Right? So that means it's gonna make a surfactant because it'll straighten out. So this, the way they draw this carbon in the picture is exactly the conformation that it can take. So that the natural state for an alkane chain is this planar zigzag, they call it. That structure is actually the structure. It isn't like a pushed out, squished down 3D thing. It's actually got that kind of planar structure when it's at equilibrium. So that's why it can crystallize the way it does. But anyway, so yeah, you could call it C18DQ8, or you could call it like a 16 carbon carboxylic acid that's got the double amino. Right, you can kind of just figure it out how they got that. Like they used ammonia here, and then they use this. They tell actually the chemistry that they did with it. The other thing that's weird is he says like the craft temperatures where it's going to precipitate out is at 0°C, which is where it's in water, you know. So it's like be hard to measure that. Like basically it would freeze before you could get to that. Anyway, so the first question in here is like figure out all the stuff he lists in here, like what's lauric acid. So that's the 12 carbon thing, and then tetradecyl is a 14 carbon. Then trimethyl ammonium is a tetra is the it's a 4-methyl stuck to a nitrogen, right? So anyway, you can Google these. Like I think you can just Google, or you can use this thing called NIST webbook is kind of useful for this kind of problem, but you might be better off just looking at Aldrich cells, all this stuff, and they have pictures of what they are, but this is a pretty good source for someplace you can search by name. And then I think you can just, I haven't done this, but it might not work, but if you put in tetradecyl-methylammonium hydroxide, it should tell you like everything about it in theory. It didn't work, but sometimes it'll work. Or you can just like put it into Google and like look for it. So it's definitely there somewhere. So whichever one you want to use. One isn't, so usually Sigma Aldrich has a picture of it. Like right there, 12 carbon chain. I mean, this is kind of, looks like it's compressed. That's actually a long oleophilic thing, right? The 12 there, and then that's the amine group at the end with the tertiary amine thing. So this guy also would cause skin irritation and mutations. So nasty things, right? So anyway, this is like some, I listed all the possible things in here. Oh, right. So laurate is a 12. That's the beef fat thing, right? And then Gemini, so Gemini is the twins, you know, for the astrological symbols. And Gemini spaceship was like 2 guys in the thing. So it's got to do with 2. It's like you got 2 Gemini surfactants. So when you have two long chains hooked together by some kind of polar group out here. It's like a bridge. It's a double bend flagella thing, whatever. So it's almost like when he puts this in, because it goes plus minus, they're going to bond more or less. This is coulombic attraction. This becomes something like a Gemini surfactant in a sense, you know. I think he mentions that in the paper. Tetradecyls, 14 carbons, and whatever. Then lauric. Lauric is also the 12 carbon, and it's got a carboxylic acid on the end. And then hexadecyl 16 methyl midazolium is like a double nitrogen, kind of a ring with double bonds on it, and then a plus on it. So you can look it up and just see if you can just kind of like copy the picture and pop it in. So you just kind of see, the point of this is that you can see, so sodium toluate, so it's toluene, so it's like a benzene ring with a methyl group on the side, and then you add a carboxylic acid group on the other pair of position, the other side of the benzene ring. And then that's one of these like additives to make the super concentrated detergent type thing. Cinnamonate, I forget what it is, like 16 carbon chain. All these are going to be like carbon chain with some kind of head group on them, right? So dodecyl's 12, that's the same as laurel. And then it's got an oxy, so it's got an ether group with the head group. And so, oxy, and then an ethyl group. So it's 12 carbons, oxygen, 2 carbons. And then this is the polar part, I guess, tetramethyl diammonium. So it's like, it's got like a, anyway, you can figure out what these are. You just have to Google each one and somehow if you can copy the picture and throw it into the, like the homework's going to be a PDF, somehow just do that. So you can draw it if you want, but it's going to be a lot of like zigzag things, right? So it might be boring. Carboxylate surfactants are those are just carboxylic acid end groups. That's basically soap. Carboxylate surfactant is the same thing as soap. So just got it's a carboxylic acid group, double bond O, and then an Na plus on it. O minus Na plus. Acetyl triammoniums. This is like the popular. This is one of the most popular cationic. So it's got methyl ammonium. So it's got N with methyls. It's a 4 bonded. So it's a tetra functional ammonium, and then 4 methyls on it, or 3 methyls and an open one. The other one goes to acetyl, which is I think 16 carbons. So this is like the most popular. So it's like SDS, which is also SL. So sodium dodecyl sulfate, which also SLA, sodium lauryl sulfate, are the same thing. That's a 12 carbon beef fat thing with a sulfate group on the end. And then CTAB is the cationic most popular one. Right, those two are, that one is the most popular anionic, this is the most popular cationic, CTAB. So the cationics are make more stable structures, and the anionics make less stable structures. And so anyway, there's some. Anyway, the cationics are used because they make more stable structures to make things like catalyst supports. So you can take silicate, like sodium silicate, which will make silica. It's a pH 14. If you bring the pH down to 7, it makes glass, right? And it's in water. So pH 14 in water, you can throw in some of this CTAB, shake it up like I did, and it spontaneously forms a structure, which is a perfect structure, perfect porous structure with nanoscale to it. Then you drop the pH and it makes glass. And then you burn it, you put it into an oven and burn off all the organics and water and stuff, and you end up with a glass, porous glass catalyst support with perfect nano-sized pores. So anyway, so that's CTAB is a basic thing that people use for that kind of process, templating organics. It's used in some consumer product stuff too. But basically I think it's popular in materials because of that templating stuff. So sodium decoate is a 10 carbon with, so it's a 10 carbon surfactant. Olate, I guess it's, I don't know, 18. Octyl, it's like something 18, I think. Anyway, you can look those up, just see what they are. The point is that like they're all pretty simple, even though the names are complicated. So just to get used to, I don't know, just to say like, yeah, these things look really complicated, but when you actually look at them, like I can identify the oleophilic part and the polar part to it, and that's how the thing functions. And then at that point, you can just say, oh, it's a squiggly line with some kind of green dot on it, green or orange, depending on if it's like plus or minus. And then I have 2 here because I have 2 there and 1 there. So that's how I'll just, but you can't think about it with those names. You can kind of think about it with the structure, but it's much easier to draw that it's a triangle, and it's going to fit in to make a sphere or make a rod if you draw that way. Right. So it's kind of like if you want to make propositions about what happens when you add a cationic to an anionic, you have to be on this level because you can't think about it on that level. Like that level tells you nothing. So you have to get in your mind like this kind of cartoon, but be able to connect back to that name. That's the point of the question, right? Anyway, this is the business I was talking about. So benzene sulfonate. So this stuff's all made in Cincinnati. Because we're like the soap capital of whatever. We're the lard capital, we're also the soap capital. So basically all these materials are made here. So P&G doesn't really make anything. They just buy components from little companies, partly because there's no liability if the place blows up, which the place in Springfield, Ohio, like 3 or 4 years ago blew up. There's two places that make benzene sulfonate. One's off 275, the other one's in Springfield. The Springfield one blew up, and like 3 people got killed, something like that. It was a pretty big thing. It was next to a school or something. The school had to evacuate. I don't know if anybody lives in Springfield, but it happened. You know, so basically that's why P&G doesn't make this stuff. They just buy it and then they mix it and sell it, put it on, figure out where to place it on the counter at the supermarket. So anyway, there's stories, disaster stories to all these chemicals, yeah. But then added to maintain, so yeah, so that's that. And then just explain kind of how that might work. Basically, it's a geometric argument. Like it's going to somehow make it fit in to make a better triangle or something. Or I'm not looking for any kind of sophisticated answer. But if you look in there's some books on surfactants. I don't know if I have any in here, but there's like a geometric model that goes with it where you can actually figure out the sizes of the different parts of the molecule, and then actually just do a geometric analysis to see how it would fit together to simplify it. You know, the problem with that is that, so it's not just geometry, it also is like thermodynamics, like the precipitation point and things. So you have, a lot of it has to do with how the water organizes around these kind of charged molecules. And there's a huge, like, so if you think that this counterion would be like a monolayer around the surfactant group on the thing, but it actually goes out like 20 Na pluses out, you know, from the surface of this thing. So if you look at that, micrograph, you know, that's what's not shown also is that the sodium is actually super organizing around this thing. So yeah, oh, there's these lines, that's it. But basically, the line is just the place where you see the organic part of this thing. But the sodium is actually sticking out like pretty far from these. So they're actually really thick tubes. They're not just the thin thing you see there. So you don't see the sodium in that micrograph, right? So if you do X-ray scattering, you see only the sodium. It's because the sodium is due to the atomic weight of the materials. So X-ray scattering, you just see the sodium. Neutron scattering, you just see the tube. And TEM, you just see the tube. So the sodium matters in a lot of ways. Like it's going to matter that it's going to lead to this really thick tube. Partly explains why they're so linear. And then also entropy, right? So if you collect all those little things and organize them, like you lose a lot of entropy. So that means it's not going to be as miscible because entropy drives miscibility, right? So the whole thermodynamics of these is going to be like how the things that you can't see are organizing in this, right? So that's kind of another twist of these worm-like micelles. Anyway, so here's overlap. All right, so principal ratio, what structures do you expect for those two weird ones? Okay, and then a lot of the curves overlap. So there's like two features to that rheology thing. So there's this one, I mean, I don't know what to say about this one. This one, like between the squares and those squares, I think it's probably Newtonian fluid that's kicking towards worm-like micelle. So you could say something like it's an elliptical. So it's going to go from spherical micelles, which would be Newtonian fluid. That's going to go to elliptical. So it's not a discrete transition from spherical to worm-like. So it's going to go stretched out a little bit, then a lot more, then a lot more. So maybe this thing might be the signature of elliptical micelles. And maybe at that point, the ellipses align or something in the flow field. And you could say some things about that. It shows shear thinning out here, but it's at a higher shear rate. So at a faster time, 1/time. So it's a faster time. So it takes time for the things to kind of pull out of their entanglements and then relax back. But this thing's, maybe you're looking at ellipsoids orienting in the flow, and then something like that. And that happens faster than the other things happening here. Then these things are all on top of each other. So that means that somehow, so rheology, even though you don't see structure in rheology, and the same rheology curve could come from two completely different structures. So there's no direct link between rheology and structure, but nonetheless, every time anybody describes a rheology curve, they talk about structure. There's nothing else to talk about, right? So basically, you say, well, what is this tail over? Well, it's a time of what? And then you start talking about structure, right? So the time for the chains to reach their kind of undistorted state is like that time, and these things all have the same time. That usually means that they're the same molecular weight, right? So you're kind of looking at, even though these things are at different concentrations and the molecular weights, the chain length is supposed to get higher with concentration. They don't do that exactly. And it should also change with the, so basically they seem to form one kind of structure. So anything, so again, like whenever you're trying to describe rheology curves, you're just going to be talking about structure, and you're basically just coming off the top of your head, whatever you think sounds right. Because there's no link between the two. There's not really a direct link, right? Even though the only way to explain it is with that kind of model. So anyway, it's that business. Just don't spend too much time on that. Basically, whatever I said or whatever you feel like saying. And then, so this question is just like, there's some similarities and some differences between this concentration plot that he has and the one that we saw in class, like this thing. So ours would be like 1 and then 3. And this one is like, kind of could be 1, but it's got this weird tail to it. And then this doesn't look like 3, but it is going up. So it isn't the same thing, I guess. Because in our case, you're changing this is a Y. In our case, you're changing the concentration, but you're not changing the structure. Like the polymer chain stays the same when you look at a synthetic polymer, and you add more toluene to it to make napalm or whatever you want to make. Right? So it's basically this thing, when you add more concentration, the chains get longer, right? Or they can reach a point where they start to branch, which lowers the viscosity, right? And then, so the reason why they're different is because of structural changes as you march across this. And in the synthetic polymer, there's no structural changes, they're glued together, right? So I think that's probably the main reason why the two differ. I mean, that's like and I didn't say like what happens actually between that one and that one that makes it jump, right? At like 10 millimolar, which is below the range he's looking at. But, or is that one, let's see, so 10 millimolar, is that this one? No, that's 20. So 10 might be like, who knows, something happens as you go up in concentration to change the structure. And that leads to that difference. So where am I now? Why is it? So this is verify, and this one's like that second plot. Yeah, too much. But I mean, can the entanglement kind of? I mean, yeah, there's definitely a transition. So that's the point where entanglements show up. When entanglements show up, the viscosity should jump like mad. And in that plot, the viscosity goes like 1, 2, 3, 4, 5 orders. So that's 100,000 times more viscosity than we had before. Right, so this is like water, and that's like glass or something. You know, so it's like a huge change in viscosity. Right? 100,000 is quite a bit. So that you'd say that's due to entanglements. Figure 6 shows cryo-TEM. Then, all right, so I showed you those walks in class, right, where we did the simulation thing, and then where that was. So that ends up with this Brownian path. That's a standard picture of what polymer looks like. And then, like, if you look at his micrographs, like, it doesn't exactly look like that. Maybe it could. If you look at the edges of this thing, so if you look at the edges, it starts to kind of look. So again, this is a meniscus. So in the middle, you get biaxial orientation. So you can think that this is being deformed, right? As a meniscus forms, it's like a lot of stress in this really thin film. And the thickness of the film is the same as the things that you're looking at. And you have this kind of boundary layer for flow, right? In other words, things when they get near a surface tend to stick to the surface. So if your surface is stretching out in the meniscus formation, it's going to make the things that stuck to it also stretch out. So, and then over here, maybe it starts to look more like that random walk picture of things at the edges where it's less deformed, right? So basically it doesn't look at all like our thing, except maybe at the edges. But basically there's a reason for that, because this stuff it's not the same thing. Like it's under stress, so it's going to deform. In fact, this would support the idea that you have shear thinning because they orient and they're gonna spring back to something like at the edges. So they're gonna go from that stretched out back to this when they get the relaxation to the thing. Anyway, so it's that business. Oh yeah, I gave a link here to that simulation thing. The samples were prepared. This is about what the problems are, like be critical about a TEM, like when someone shows you a picture. One thing, right, inside, so this is all right. So this thing across this is 200 nanometer, right? So and you can see there's like a few chains here. So maybe you can get like 100 chains in this picture. And inside the actual sample they did the rheology on, I mean, there's going to be billions, hundreds of billions of chains. Because this is a thin, it's going to be 3D also. It's not just expanding it that way, right? So anyway, so looking at one chain here and saying, I see an entanglement, I see a branch. I mean, you could see a lot of things, like I see these little dots too, and like, so you could see a lot of things, and this might not even be one like my cells for all you know. You know, you could be looking at something else, who knows what. It's at 70K. So what structural things form at 70K, like a lot of weird stuff, probably. Superfluids or who knows what. You know, superconductors, whatever. So anyway, I don't know. I mean, basically, you got to be critical about micrographs because you're just looking at a couple. But on the other hand, like I said about the rheology curve, like you're always going to argue about the morphology to explain the rheology, even though there's no link, no real link. So you need to have a picture of one of them to say like what it is that you're looking at in the rheology curve. Because rheology, you can just slop the goo into the machine, click it on, walk away, come back, and you got that curve, right? Like anybody could do it probably. I mean, so, and basically you can get a nice shear thinning curve like that. So anyway, so you have to have a model to go by, and the micrograph gives that to you, but you have to be really skeptical of micrograph. Like you have to be really critical when people are showing you one thing that you have trillions of. Because I mean, out of a population of trillions, you can always find one that's going to fit whatever picture you want to do for it, right? Like, oh, they branch. Yeah, I can see branches. You know, so but I only see one branch. So that's kind of an issue here. That's it. So that's a quiz. Any questions on this thing? Or... Yeah.
I think the Canvas assignment is still set to close at.
Yeah. No, it's Tuesday.
Okay.
Yeah, I didn't change the thing online.
Okay.
But
So it's the assignment's due Tuesday.
Yeah.
Okay. Awesome.
Yeah, it's kind of like I mean, it'd be good to have things in, you know, but basically, no, it's due on Tuesday. So I changed the date on it. I just didn't get a chance to do that.
Awesome.
So, yeah, so hopefully that'll work out. And it might be like, we'll just go Tuesdays, I guess, because it's going to be too close, right? Otherwise, what do you think?
I have a lot of like weekend commitments.
All right, so we can do Tuesdays. Is that better? All right, so let's just say Tuesdays. I mean, it doesn't matter to me that much, except that, I mean, it'd be nice to do it. Anyway, I can do it on Wednesday instead of Tuesday. I'll maybe like spend 10 minutes talking about whatever thing is.
I don't have a preference like week wise, because I feel like my classes, I get more busy like Wednesday through Friday. Like the beginning of the week, it like isn't busy, but like.
Oh, okay.
Busy for me.
All right, that's good.
I'm different than everyone else.
Yeah, well, hopefully that's okay with everyone. I don't know, and then so you have to find your groups, and then like, did anybody contact the group people? Or maybe you know them already. And then I don't know, do you guys usually do it like online or something, or do you meet in person, and what do you do?
One group has it shared over a OneDrive.
Okay, so you don't even talk to each other.
We can talk over the email and stuff.
Okay, all right. I mean, the nicest thing would be like, all right, if everyone did it and then compared answers, that would be sweet. That would be the perfect scenario. And then you could decide like which one was the best one. And then you maybe learn something from the other people, especially if there's a grad student mixed with undergrads. So, but I don't think that ever really happens. I don't know how to really make that happen. Like, so if you have any ideas about how to make that happen, or if you don't think that's a good idea to do that, that'd be a good thing too. basically, it's easier for me to have fewer homeworks coming in, and I found out that it didn't make any difference for the grades, like because if you mix the groups randomly, believe me, you will end up with the same grade. Because some weeks you'll be in a bad group and some weeks you'll be in a good group. What it does is that the people who are gonna flunk won't flunk, they'll get like a B, you know, and then the other people will still get an A. So it relieves the problem of people like flunking out. And then, so it solves a couple problems. It's less work on my part. Everyone gets the same grade except the low end doesn't fall out. And then it seems like it would be an opportunity to kind of learn from each other. That the last point doesn't seem to happen. So I don't know. Usually people would just divide up the questions. And then you do that one, I do that one, I do that one, and then just file them together. Which seems kind of like, and anyway, I don't know. If there's some way to do it another way, let me know, but I'd like to stick with it though this way, because I think that it's good. At least you know people's names and you can figure out like who does stuff and who doesn't, that kind of thing. Maybe you already know that, but so, all right, that's it. So have a good long weekend.
I still don't know the names of classes. The only class names I know.
So we're trying to do the synthesis of vanilla.
Yeah.
We're wondering if you had two or a few yourself that worked on. Lignin.
Yeah.
Like, not
We were just wondering, like, so, yeah, you could probably.
The synthesis route that we've chosen starts
Yeah.
with like a wood smoke byproduct.
Well, I know a guy at International Paper in Seattle, he can email, ask him stuff.
Sure.
But he would know, he might know like right off the top of his head.
We're just looking for like a specific lignin or lignin got like that.
Yeah, that'll be a good question to ask.
Okay.
There's also International Papers, like right on in Loveland on top 275. They have, that's their research. But they're good people to talk to. I might have their email too. This is this guy's email. We just send him an email and see if he doesn't respond. It's like Abby.Prasad, Prasad. And then it's at I was gonna pick up just, I would ask him, I would say like, we're doing this thing at Lignan. Is there anybody at International Paper that could tell us about whatever your question just was? And he might be able to come back and say this, and this. We might say, email this guy to Schmo. He's in Cincinnati. He's like 10 minutes from you. You know, and maybe it might be worth going over there because it's a nice research lab. It's not a production, it's like a research lab.
Is it all right if we CC you on that first email?
Yeah, you can tell him I mean, he won't know that we got something.
Perfect.
It's on contact here, I think so.
Cool. Thank you.
I got a question about homework. I sent you an email, but I want
Yeah.
to talk to you directly. Is it okay if I?
I'd rather have you just do it with the group, you know, like just,
Yeah.
they're all doing it just by email, like it isn't, there's no time commitment, you know? I don't think, I think you'll do, if it looks like you're getting a lower grade or something. I mean, probably everyone's gonna get an A in the undergrad, you're an undergrad, right?
Yeah.
Yes, I mean, basically, probably you guys are all gonna get an A, you know? So I wouldn't worry about the grade, and it's gonna be easier on me to not have